Hey everybody, welcome back to Environmental Organic Chemistry with Lisa. So we're going to finish up the discussion of hydrolysis by talking about the Swain-Scott model, which can be used to predict the rates of SN2 reactions. So Swain and Scott developed this model a long time ago, 1950s I believe. And what they had noticed was that if you plot something like this, where this is the second order rate constant for a hydrolysis reaction, a nucleophilic reaction, second order rate constant with units of per molar per second. If you plot the rate constants for the same chemical with different leaving groups, so like this could be methyl fluoride, methyl chloride, methyl bromide, methyl iodide, and you have different nucleophiles. Here's water, here's fluoride, chloride, hydroxide, cyanide, and thiosulfate, that you get these characteristic type reactions, and the distance between these 2 points is the same as the distance between these 2 points, and that becomes the basis for the Swain-Scott model. So the Swain-Scott model is saying that the log of the rate constant of the reaction that you're interested in divided by the log of the rate constant of a similar reaction, a reference reaction, is equal to N, which is the strength of the nucleophile, times S, which is the susceptibility of the backbone, the carbon backbone, to this kind of attack. And so what becomes really powerful about the Swain-Scott model is that it is a way of quantifying how strong each of these nucleophiles is by giving it an N value. So this has been done for two references, one using methyl bromide in water and the other using methyl iodide in methanol. And you can imagine, you get slightly different numbers in each of these two systems, but they're not that different. So water is defined here as having a nucleophilicity of 0, whereas in this methanol system, here water is the solvent, so the solvent is defined as having a nucleophilicity of 0, but here the methanol is the solvent, so again the solvent is defined as having a nucleophilicity of 0, and then you go in increasing strength of the nucleophile as you go down these tables. But you notice that the order is the same: nitrate, then fluoride, then sulfate, nitrite, fluoride, sulfate. So there's a lot of similarity between these two sets of nucleophilicity values, the N values, and in fact we can plot them. Here's using the methyl bromide, and here's using methyl iodide as your reference, and you can see that the correlation is quite strong. The R squared is 0.98. There's a little bit of a difference in the slope. Slope's not 1, it's 0.68. But nevertheless, it doesn't really matter which of these two reference systems you use. You get the same ordering in terms of the strength of the nucleophiles. So this is where we got the table that I showed before, just showing that there's some chemicals, some species that can be very strong nucleophiles out in our real world. Of course, nitrate is a common pollutant that you find in agricultural runoff. Fluoride, not terrifically common, but there's a little bit of that in seawater. There's quite a lot of sulfate in seawater. Of course, carbonate is going to be present in all natural waters. Phosphate can also be present in natural waters, usually as a contaminant due to agricultural runoff and use of fertilizers, but could be there for more natural reasons too. Here's acetate. Chloride, of course, chloride is going to be present in seawater at 0.5 molar, which is pretty high concentration. But chloride could also be present in freshwater at lower concentrations due to the use of road salts in the winter, back when we used to have a winter, and we would put salt on the roads because they'd get slippery, because in the winter you had this white stuff called snow, and it was frozen water. I know I'm blowing your mind. And it would fall on the roads and make the road slippery, and by adding salt you could melt the water and make the road less slippery. Pyridine is a building block of a lot of organic molecules in living things. And so as those living things die and decompose, they can release pyridine. Here's aniline. pH means a phenyl group or a benzene ring with an NH2 on it, so that's aniline. Here's phenolate. Now that you understand all about acid-base chemistry, you understand that phenol can lose a proton to become phenolate. That's what this is. We have bromide, azide, cyanide. This is a diethylamine. Remember, it's got lone pair electrons here. that can act. That's why it's a decent nucleophile. Iodide. And then here we have bisulfide. We've got some thiosulfate, and we have some organic matter that, like benzene rings with sulfur groups on them. So these can be the products of biological decay, especially anaerobic biological decay. And look at the magnitude of their N values. And remember from the equation here that this is on a log scale, right? So when you're saying that bisulfide has an N value of about 8, and water, or in this case we're using the methanol, but methanol has a nucleophilicity value of 0, then you're saying that bisulfide is 9 orders of magnitude, or 8 orders of magnitude more powerful as a nucleophile than the methanol. So these are incredibly powerful nucleophiles, and you're going to find those in reducing environments like marshes, saltwater marshes, where you get anaerobic conditions. You're also going to find them in places like sewers. That's why sewers smell bad, because of all those reduced sulfur species. And they can be very, very strong nucleophiles and can cause all kinds of interesting chemical reactions with chemicals, pesticides, herbicides, all kinds of anthropogenic chemicals. So from this, we could also calculate the concentration, using this equation and trying to calculate the rate constant of a reaction with some nucleophile compared to the rate constant of the same reaction with water. We could use this to calculate a rate constant at which the rate of reaction with water is the same as the rate of the reaction with a nucleophile. Okay? And we call that 50%, because we're basically saying what concentration of the nucleophile would have to be present for the reaction to be equally fast with that nucleophile as it is with water. And so for something like nitrate, you would need like 6 molar nitrate. That's incredibly high. If you got 6 molar nitrate, you have much bigger problems than nucleophilic reactions. Fluoride, this is still quite high, 0.6 molar. That's not going to happen. Sulfate, maybe you'll get there. Chloride, you're definitely going to get there in seawater, right? Seawater is already 0.5 molar. So in seawater, chloride can outcompete water as a stronger nucleophile. Carbonate and phosphate can sometimes achieve these levels where they become important nucleophiles. This is not an uncommon concentration that you might find for bromide in seawater. Now, this hydroxide concentration is 4 times 10 to the minus 3 concentration of hydroxide. If the hydroxide is 4 times 10 to the minus 3, then the protons are somewhere around 10 to the minus 11, which means that the pH is around 11. So it has to be extremely basic in order for hydroxide to get to the point where it can outcompete with water. And so for most pHs, kind of the normal range of pH we expect in the real world, we're not going to see that hydroxide is a terrifically important nucleophile. But iodide in some circumstances can get up to these levels. And then for things, again, like hydrogen sulfide and thiosulfate, and this is a polysulfide. It's got 4 sulfur groups in a row, 4 sulfur atoms in a row. These can definitely build up to reasonable concentrations in anaerobic systems where they're actually competing with water in terms of nucleophilic reactions. So what factors determine the nucleophilicity? Well, in order for the nucleophile to attack your substrate, first it has to leave the solvent. That's not something you think about very much. But when these compounds, chloride, fluoride, bromide, when they're dissolved in water, they're surrounded by water molecules. And in order for them to attack some, carbon-based life form, they have to get rid of their sort of entourage of water molecules so that they can directly attack the substrate. And I mentioned before that fluoride is extremely well solvated because it's such a tiny little atom. It's really, really small. And to have that negative charge localized on such a small area is very unfavorable. And so the water molecules surround it and basically kind of spread out that negative charge. But as a result, fluoride is really not a very good nucleophile. You can see it's over here on the left side. It's a worse nucleophile than chloride or bromide or iodide in water. Again, if you look at Khan Academy, they'll tell you that fluoride is a very strong nucleophile. That is true in other solvents, but in water, fluoride is not a very good nucleophile. Chloride's okay. Bromide and iodide are quite strong nucleophiles. And by the same token, Hydroxide is a weaker nucleophile than bisulfide, the hydrogen sulfide having lost a proton. So this is actually quite a strong nucleophile, and it smells bad. It's, hydrogen sulfide smells like rotten eggs. So we do see a fair amount of that in anaerobic systems in the environment. So the ability to leave the solvent and attack the reaction center, and then also the ability of the bonding atom to donate its electrons. And so sulfur is bigger in diameter than oxygen. It's a row lower on the periodic table. And so because it's bigger, its electrons are a little bit further away from the nucleus. So it's a little bit more easy for that to donate those electrons to the carbon that it's attacking to form that bond. Whereas oxygen, because it's smaller and holding on to its electrons a little bit tighter, it's less able to donate those electrons to form a bond. S is the other parameter in this equation, and the short version of S is that you can assume S is equal to 1. Sometimes it does range from, maybe 0.83 to 1.2. There are some very strange reactions with, chemicals where it can sometimes go as high as 1.6. And unfortunately, there's some of those chemicals for which it can go that high are environmentally relevant, like allichlor and propichlor, because they are pesticides. But most of the time, you can just assume that S is equal to 1 and not worry about it.